Up until this point in the year, we've dealt with forces that exist between objects that are in contact with each other. They push, they pull, they rub on each other. It's not hard to see where the force comes from. The forces we're going to be most interested in for the rest of the year aren't like that. In fact, they can act at a distance. I'll give you an example. Here's the Earth. We know the sun is very far away from it. And yet the sun is what's making the Earth orbit, go in a circle. How's it doing that? We know electrical charges put forces on things. Protons push on each other. They pull electrons. You may have noticed that your hair stands up on the back of your hand right before you get shocked by a doorknob in the winter. How does the doorknob know your hand is there? How does your hand know the doorknob is there? There must be some force acting across this distance, and it's those kind of forces we're now interested in. So, if we talk about the force of gravity in particular, it seems to have a pattern around the Earth. I'm sitting here in Connecticut, United States, and the force of gravity on me is down. Somebody in India, the force of gravity would be down. Someone in Australia, the force of gravity would be down. Someone in Bolivia, it would be down. But for all of us, down is different. Because really, down for all of us is pointing in towards the center of the Earth. So we know that the force of gravity varies around the Earth, but it's always directed inward. What's the difference between the force of gravity here, or here, or here? We know gravity exists in those places. But is it the same? Is it different? That's what this unit and this lecture is supposed to be about. So, it was figured out over a large period of time, from the 1300s all the way up through the 1600s, that gravity, static electricity, and a bunch of other things spread out from their source in a very particular pattern. And that pattern is known as the inverse square law. The easiest way to see it is to imagine throwing a rock onto a very still lake. So let's do that. All right, so I'm going to throw this rock into the water, and I want you to watch the pattern that the waves make. So as you can see, they're circular, they're spreading out, and as they get farther and farther away, they seem like they dissipate. And that's because they're spreading out over larger and larger space. All right, so I hope you saw what those waves did. They started to spread out. In larger and larger and larger concentric circles. And the waves were very large near where the rock went in, but their energy spread out over larger and larger and larger circles, and therefore the waves weren't as high the farther and farther away you got. It's like they dissipated over a larger and larger space. That idea is the big idea on how gravity, electricity, and some other things like light spread out. Let's look at the force of gravity, for example. We're going to see that gravity is caused by things that have mass. So we've got the Earth in the middle of this sphere. So this imaginary sphere on the outside, which usually gets used to teach astronomy, imagine we were standing on it. The Earth is pulling on me, and it's pulling, or it could be pulling, on an infinite number of other people all around this plastic sphere who are the same distance from the sphere as I am. Now, imagine the sphere got twice as big. There's so much more surface area now for people to stand on. Each of them would still get gravity from the Earth, but it would be a diluted gravity. The gravity would have diluted because it would have spread out, just like the waves from that rock being thrown in the water spread out. So, if you think about what I'm talking about, this is area. I'm running my hands over it. We could tile this with floor tiles that have length times width. So, as you get farther and farther away from the center of that sphere, the surface area of the imaginary sphere you're standing on gets bigger. What's surface area? Well, for a sphere, it's 4 pi r squared. So as you move a distance r from the center, gravity spreads out by a factor of some number times r squared. So that led people to propose the idea of the inverse square law. It says that as you spread out, the force of gravity is proportional to 1 over r squared. Now, the electric force does the same thing. And many other things do too. So I hope this makes intuitive sense. As you move away from a point object, the effect is being spread out over a larger and larger area, so we get a smaller force of gravity, a smaller electric force. So it's one thing to understand the inverse square law and think it makes sense, but it's another to actually test it and show this is what nature does. This idea of testability was a problem for scientists as they tried to find out whether objects actually follow the inverse square law. The idea is old. It goes all the way back to medieval times. But by the 17th century, scientists were trying to see if this applied to things like gravity. The famous British scientist Robert Hooke wrote to Isaac Newton and said he thought gravity spread out like this, and he would like Newton's help in showing that that was true. This began kind of a race between the two scientists who were very famous and competitors and didn't really like each other very much. And there was a lot of acrimony when Newton was eventually able to show that gravity does this. We'll talk about that later. But for other things, it actually is easier to show this. But one that's actually easy to test, and we can do it right in the classroom, is to talk about how light and how bright light appears spreads out. It seems to follow the inverse square law too. So in other words, light's going to seem brightest close to a candle. As we get to larger and larger radiuses, it's spreading out over larger and larger surface areas. Again, surface areas that look like this sphere. And that means each location appears to be getting a dimmer light. So let's test that. This box is a really cool device for measuring the relative intensity of two light sources. And the reason that's important to us now is because of how light spreads out. So I'm going to light these two candles. I'm going to light this one here. And I'm going to put them into the box. And as you can see, there's a device here that slides up and down. And what this lets us do is it lets us find a balance point for where the light from the two candles appears to be just as intense as the light from the one candle. Now obviously we have to do this in the dark to get any sort of meaningful result. So we'll open up our doors. We'll see what's inside. And what we're looking for is the place where the light balances. We can tell if the light's balanced by looking at the little window that's shaped like a star. And one of the sources I found that told me how this worked, which is a link is given on the Flickr album, it says you look for when the window has the same brightness as the surrounding circle. And you want that to be true on both sides. So we found it for here. And that's at about 58.3 centimeters. So you can see that right here. Actually 58.8. So let's check and see if this balance point has any sort of useful information about how light spread out from our twice as bright source from our half as bright source. Oh, I forgot, safety is important. So anyway, you can envision that light is spreading out from this source in spheres. So anyway, if light spreads out according to this inverse square law, then we expect there to be a relationship between how far we are from our twice as bright candles and how far we are from our half as bright candles. So let's try to use this law to predict where that space will be and see if it actually corresponds to the 58.8 centimeters we found. Other thing we need is that this is actually 0.588 meters and that the entire distance was 1 meter. So let's predict where the spot should be, where our brightness should be equal. So we're going to say our two candles. We want to find out what distance r from them. The brightness from one candle is the same. So we don't know what r is, but we're proposing this inverse square law because we expect it has spread out over a larger and larger area. We don't know what the relationship between, we don't know how far this distance is either, but we do know the whole thing was 1 meter, and that therefore the distance from our two candles has to add to the distance from our one candle to give us 1. So those are both squared. I'll spare you the math, but I just squared that binomial. I cross multiplied to get this, and I got this equation here, 2 minus 4r plus r squared is 0. Did the quadratic equation, and I got two answers, but only one of them makes sense, 0.586 meters. The other one is outside the box, basically. It's 3 meters down. But it's very close to what we actually measured. So that's light. What about gravity? And Newton understood that you would actually need to measure gravity spreading out. Now, how would you do that? You would need to have something close to Earth where you know something about the force of gravity, and something far away where you could find out about the force of gravity and compare them. Well, on Earth, we know that the acceleration of gravity is g, which on Earth is 9.8 meters per second squared. What if you go away from Earth? Like, say, out to the moon. What's the acceleration of gravity out there? Well, we know that the moon has the force of gravity acting on it. We know that it's moving in a circle. So can we figure out from those two pieces of information whether the acceleration of gravity has diminished out there? Something that would help us see that the inverse square law is true? Well, we can, if we consider it a circular motion problem. We write sigma f is ma. We don't know the mass of the moon, but it doesn't matter because we know that the only force is the force of gravity. And what is A if you're moving in a circle? Well, of course, it's v squared over r. What's the force of gravity? Well, it's m times whatever the acceleration of gravity is out there. So, can we find out what the acceleration of gravity is out there? Absolutely. We don't even need to know the mass of the moon. Gravity's just going to be so if Newton could find those two things, he could see what the acceleration of gravity is way out there and see if it diminished. So we've got that same drawing before. We have the moon orbiting Earth. The same calculation is here. And we can see that the acceleration due to gravity is v squared over r, just like we saw a minute ago. The best description of this in writing is Randy Knight's Physics for Scientist and Engineer. And this calculation here is inspired by that. What we're going to do is we're going to step-by-step figure out what the velocity of the moon is, and then figure out its distance from Earth. So, as far as the velocity, we know that the velocity equals distance divided by time. And if you're moving in an orbit around the Earth, the distance of an orbit is the thing's circumference, and the time is the period, or how long it takes to do a complete cycle. We know about the period of the moon going around the Earth. It's a month, and a month on average is 27.3 days for the moon to completely come back. How about the radius? That was actually known in ancient times too. You could actually use something called parallax to figure out how far the moon must be away from the Earth. So in the late 17th century, when Newton was coming up with these ideas, those two numbers were available to him. And that's all you need in order to figure out how fast the moon is going. Okay, so here is me taking the 27.3 days and converting that into seconds. And then I'm doing the circumference over time equation equals velocity. So I get that the moon's velocity is a little more than 1,000 meters per second. And then plugging into g is v squared over r, we end up having the Earth's acceleration of gravity as far away from the Earth as the moon is really small. It's about 0.003 meters per second squared. So gravity definitely decreases as you get farther away. And Newton was wise enough to realize that he could see that just by looking at how the moon moved. And that's why he gets the credit for discovering this rather than Robert Hooke. So what Newton was interested in was not so much what the value for gravity as far away from Earth as the moon is. He was interested in how many times smaller it was than on Earth. And what he knew was that if you were standing on the surface of the Earth, your distance from the center is 60 times smaller than the distance of the moon from the center. The moon is 60 times farther away from Earth than you are. But if you divide this 0.00272 meters per second squared by the 9.8 meters per second squared you're experiencing as the acceleration of gravity, you see that it's about 3,600 times smaller. What relationship do 60 and 3,600 have? They're 3,600 is the square of 60. So you got 60 times farther away. Gravity decreased by 3,600. So that was how Isaac Newton showed that gravity decreased just like light does according to the inverse square law. He had to measure something far from the Earth and something close to the Earth. He compared their accelerations of gravity. The acceleration of gravity on Earth is 9.8. It's 0.00272 out as far as the moon is. The moon is 60 times farther away, but gravity is 1/3600th. So that is justification for the inverse square law.